second quiz, October 31st. As you might have expected that, since I'm going to ask you to show the Cauchy-Riemann conditions for some functions, so probably it'll take 2 hours. So 3, 16 to 18. So it's going to be 2-hour quiz. And before the quiz, I'm going to have a 1-hour class, and then after that, so you can prepare 2 pages of cheating sheet. And you need an engineering calculator. I mean the real calculator that can calculate the sine and cosines with various angles. And you might need a dictionary. But no smartphones are allowed. Skeleton. So no smartphones are allowed. So if we refresh our memory, then the condition that the complex function is differentiable is the real and imaginary part should satisfy the Cauchy-Riemann conditions. So if the condition for Fc to be differentiable something is wrong with the spelling. Is partial x, partial u, partial y, partial v, partial y, partial u is minus partial x, partial v. So if the complex function fz satisfies this Cauchy-Riemann condition, then we call that fz is analytic. This is called Cauchy-Riemann condition. And we say Fz is analytic. So when Fz is differentiable, then it satisfies Cauchy-Riemann condition, and we say that the function is analytic. And I have shown that the sequence x satisfies Cauchy-Riemann condition, right? So, etc., etc. Now, the question is what if Fz is of the form of course, fg is a function of x and y, but through the function r and theta. Theta is arctangent to y over x. So in this case, of course, we can calculate the Cauchy-Riemann condition in xy, but if it is possible to represent in terms of more simpler form like r and theta, for example, we have the principal value of ln z is given by ln r I theta, right? So in this case, whether we can show that it is differentiable or not. That's one question. So, if you remember your first freshman calculus, then the partial x, partial u is in this case partial r, partial u, partial x, partial r, partial theta, partial u, partial x, partial theta. And actually, you should have learned in your freshman years in Vidokuna, right? But you don't remember? Do anybody remember that? That's the tricky part, right? So let's go back to the original definition. So partial x, partial u is actually delta goes to 0 over the delta u r x plus delta y you should have learned in your freshman calculus, 미적분학, but just for probably most likely you don't remember that. So I'm going to briefly derive this. And theta x plus delta y minus u, of course, r x y theta x y. And wisdom is, if you have some complicated situation, you can do nothing, right? So let's try to add something 0 and see what happens. So I'm going to put minus u r x y theta x plus delta y plus delta goes to 0 delta u r x y theta x plus delta y minus u r x y theta x y. And I don't have enough space, so I'm going to copy this part and edit, copy to the paste, and then so delta x x theta x. Then rebound. I'm going to move this. Oh. Okay. How about that? So that's your partial x. U. Of course, we have delta. So we can actually use this r x plus delta y, r x y plus delta r, theta x plus delta y is theta x y plus delta theta. So the first term becomes this. Delta goes to 0. Delta u r x y. We can simplify without writing r plus delta r theta x plus delta y minus u r theta x plus delta y. I intentionally left that part. And then you can divide by delta r, right? And probably it's okay to move this delta. They say delta x, maybe delta x, delta x, delta x, delta x, delta x, delta x. Okay. Plus delta goes to 0. Delta theta u r theta plus delta theta minus u r theta. We have delta x delta theta. And when delta goes to 0, we also know that delta r goes to 0. Delta r goes to 0. So it becomes, so what is this part? This part. This is partial r, partial u, right? This becomes partial x, partial r. This part becomes partial theta, partial u. This part becomes partial x, partial theta. So probably in your freshman calculus class, you might have done more rigorously to derive the chain rule, but I can do very simply, graphically here. So eventually, we have this. Partial x, partial u is actually partial r, partial u, partial x, partial r, plus partial theta, partial u, partial x, partial theta. So the Cauchy-Riemann condition becomes, can I move on? So if z is u xy plus I free xy, but through some function rxy theta xy plus iv rxy theta xy. Then partial x partial u is partial r partial u partial x partial r plus partial theta partial u partial x partial theta. Likewise, partial y partial u is partial r partial u partial y partial r partial theta partial u partial y partial theta. Partial x partial v is partial r partial u partial x partial r plus partial theta partial v partial x partial v theta. Partial y partial v is but same way, partial y partial v partial y partial r plus partial r partial v partial theta partial y partial theta. So we only need to calculate. We still need to calculate partial x, partial r, partial y, partial r, partial theta, partial r, partial x, partial y, partial theta. So all you need to calculate the four derivatives, which is not very difficult, right? So let's start with r. R is, as you know, where x squared plus y squared. So this is a complex function g. So you can use chain rule again to calculate this. Partial x partial r is dg dr partial x partial g, right? That is dg d g1/2 partial x partial g. And we have derived the square root of x is what? You don't know, right? You still do not know how to differentiate square root of x. Actually, we have done that. So what is this? Dx to the half. You know how to derive this formula? You know the result, right? Because you memorized it. 1/2 x to the minus 1/2, right? Everybody knows that. But do you know why this is this? So x 1/2 is actually delta goes to 0. X plus delta 1/2 minus x 1/2. Delta goes to 0 divided by delta. This is x 1 plus delta over x 1/2 minus x 1/2. And we have derived this previously, right? Numerically, as Newton did. So it becomes delta goes to 0, delta over x 1/2 1 plus 2x over delta minus x 1 half. So this cancels each other and it becomes 1 over 2 x half times 1 over x. So 1 over 2x minus 1 over x. So if we differentiate root 2x, it becomes 1 half times 1 over square root of x. So even though you probably have memorized this formula in high school days, now you know why this is true. Right? So, can I go on? So now we can calculate this. Partial x squared plus y squared 1 half. So if we put this as g x y, then it becomes d to the 1 half times partial x partial g. And now this is easy, right? This is 1 over 2 square root of g times partial x squared plus y squared square root of g over x, and this is what? R over x cosine theta. How about partial y, partial x squared plus y squared 1 half, partial x partial r, partial y partial r. Likewise, we have, now we can calculate it easily. That's y over r sine theta. So out of 4 derivatives, we already have solved 2. So we have 2 more, which is only arcsine. So what is this? Partial x partial arctangent x, y over x. So let's do some simple side tricks. So let's say G is tangent minus W. Then W is what? Tangent to G. So dG dW is one plus tangent square G is 1 plus W squared. So W over dW over dG is 1 plus W squared. That means, so we have this. Dx, d tangent inverse x is 1 plus x squared. Right? So we now have 2 more relations. Can you continue? Can I continue? Do you need to copy? So theta is arctangent inverse y over x. So let's say this is h. Then partial x partial theta is th d theta over partial x partial theta h. And th d theta is 1 over h square, as I have done there. Partial x partial y over x is 1 plus y over x square minus x square over y is, what is x square plus y square over x square minus x square over y. So this is x square plus y square minus y, or minus r square over sine theta. Oh no, just r. Likewise, partial y, partial theta, it's the same thing. Th d theta, partial y, partial h. But in this case, 1 plus h square, 1 over x, x over x square plus y square is cosine theta over r. So you memorized everything? Can I come back? So we are ready to derive Cauchy-Riemann condition in polar coordinate. I will give you time to copy. And quiz covers from whatever we left from previous quiz until today. So today's class is also part of the quiz. So pay close attention. So let's summarize. Yes. So partial x, partial r is cosine theta, right? And partial y, partial r is sine theta. Partial x, partial r is minus r of sine theta over r. Partial y, partial r is r over cosine theta. Let me see. So, Cauchy-Riemann condition. Partial x, partial u is partial y, partial v. Or partial r, partial u, partial x, partial r plus partial theta, partial u, partial x, partial theta. This happens to be partial r, partial u, cosine theta plus partial theta, partial u, minus 1 over r sine theta. Has to be the same as this. Partial y, partial v, partial r, partial v, partial y, partial r plus partial theta, partial v, partial y, partial theta, partial r, partial v, sine theta plus partial theta, partial v, r over cosine theta. So we can combine the cosine term with sine term. So we can combine them into two. Partial r partial u minus 1 over r partial theta partial v cosine theta plus partial theta partial u plus minus partial r partial v sine theta equal to 0. And this relation should be true for theta for. So what would be the condition that this relation is true for theta? Then the coefficient of sine and cosine should be 0, right? If this is going to be 0 true for any theta, then the only possible condition is this. Partial r partial u is 1 over r, partial theta partial v, and partial theta partial u is minus partial r partial v. So this is your new Cauchy-Riemann condition for polar coordinate, and you obtain the same thing from the second equation. So I'm going to show this as a homework. So I might ask you in the quiz to show that that is true. For the second Cauchy-Riemann condition. And partial r partial u is 1 over r, partial theta partial v is equal to partial r partial v minus of that. Okay, so I think I'm going a little bit too fast, right? So let me summarize. So partial x partial u partial y partial v. This condition gives partial r partial u is 1 over r partial theta partial v. Partial r partial v is minus 1 over r partial theta partial u. Let me check. And second, we have a second equation, right? Partial y partial u is minus partial x partial v. And you can show that the same kind of Cauchy-Riemann condition in polar coordinate is obtained. Partial r partial u is 1 over r partial theta partial v. Partial r partial v is minus 1 over r partial theta partial u. So I'm going to leave this as a homework. And you had better do it homework, because I might ask you in the quiz. I feel a little bit warm, so I'm going to take off my jacket. So we can check whether the principal value of log is an analytic function. So when fc is ln this is principal value, right? Is ln r plus I theta This is your u, this is your v, and partial r, partial u is what? 1 over r. 1 over r, partial theta, partial v is 1 over r, partial theta is 1 over r. So the principal value of logarithmic function is analytic, right? So it looks like I'm going a little bit too fast, so maybe I'm going to stop here for a few minutes and give you time to digest the material. Okay, I turn on the recorder. So you say recorder in French is magnetophone, but it's nothing to do with this class. So we find the conditions for the function to be differentiable, that's Cauchy-Riemann condition. And we have done most of the differentiation thing, then next step is integration. So we need to define some terminologies. We put domain. So domain is a region. It's a region or set of a point. Even I think my handwriting is terrible. So domain is some region or set of points. We call this domain. And you can call C is a boundary. Closed curve enclosing a domain D. So C is some kind of closed curve that encloses the domain. Then you have a very famous Cauchy's integral theorem. This is a fundamental theorem, actually. If Fz is analytic in D, then for any closed curve C, which encloses the domain, the integral, closed integral of C dz is 0. And it is named is Cauchy's integral theorem. So if you have a domain, and in domain is just a region, some area, and if Fc is analytic. Fc is analytic means Fc satisfies Cauchy-Riemann condition. Then the integration is 0. Very simple, right? Something is 0 is very nice. That is always nice. So we need to prove this statement. Proof. So we say Fz uxy plus iv xy, then dz is dx plus idy, right? So closed fc dz means u plus I free dx plus I dy u dx plus I free dx iu dy minus free dy. So we can separate the integral as a real part and imaginary part. U dx minus free dy plus I free dx plus u dy. And actually that integral, closed line integral, is also a topic for this quiz. And it's related to Stokes theorem. Remember that? Right. What is the Stokes theorem? Let me see. Fx dx fy dy is, what is that? Partial y, partial x, partial y, right? Fy minus partial x, partial fx, partial x, partial y, partial x, right? Dx, dy. Remember this formula? And actually you should remember that because this was part of this quiz. So let's say this is A, simply this is A, this is B, then this is B, this is A, right? So Stokes theorem can be written as this, but also we need to copy this. Edit, copy, and then move on to the next page. Okay, leave out. Oops. So this is actually just, oh no, FCDZ. And by the way, from Stokes theorem, we have A dx plus P dy is partial x partial b minus partial y partial a dx dy, right? That's Stokes theorem. That is always true when we have closed integral. So we are going to apply this theorem to the above result. So let's first see this one, this u dx minus free dy. So this is your A, this is your B, right? So using Stokes theorem, this becomes partial x partial minus free minus partial y partial u. This is what? This relation must be familiar to you, right? This is one of the equations of Cauchy-Riemann condition. So this has to be 0, right? Because I told you that we assume that Fc is analytic in the first place, so this has to be 0. Cauchy-Riemann. How about second integral? Now it is 3 dx u dy. How about this? The real imaginary part. 3 dx plus u dy. So this is your b, this is your a, right? So applying that Stokes theorem again, we have partial x partial u minus partial y partial v dx dy. And this is what? Okay? 0 because of Cauchy-Riemann condition, right? So real part is 0, imaginary part is 0. So we have zero when Fc is analytic inside of C. That's very important. Inside of C. When Fc is analytic inside of C, in closed circle, closed curve, then the closed integral is 0. And, well, so what? So we have an integral which is 0. So why we are learning that, right? You can ask that question. And we will soon go to that topic. So this is actually one of the most powerful mathematical theorem that has discovered in the first 500 years. Something is 0, so that's what? So what? But just be patient. We are going to learn why it is so important. So we know that once Fz is at 0, then the integral is 0, right? So what if not? That's the question that we like to ask. So we can consider, so when Fz is not analytic, for example, when one over z so now your curve is unit circle. Can you say that Fc is analytic inside of the circle or not? One over z is differentiable, right? It satisfies Cauchy-Riemann condition in most of the region, except origin. So Fc is not analytic. At c equal to 0, right? So this function does not satisfy the condition for Cauchy's integral theorem as a result, right? So Fc does not satisfy the condition for Cauchy's integral theorem. The Cauchy's integral theorem requires that fz is analytic inside of every point in the region, but this function is analytic most of the points, but not at the origin, right? So then, what is this value? So it may not be 0, right? Because fz is now not analytic at the origin. So we can do some trick. C is our exponential I theta. Because we have said C is a unit circle. So unit circle, point on the unit circle. So unit circle is a circle with a radius of 1. So z can be here, right? Here. So dz. So in this case, only variable theta. So exponential I theta, I. Theta can be changed to 0 to 1, 2 pi. So closed integral z over dz can be changed into 0 to 2 pi. dz is I, 2 exponential I theta, d theta. And 1 over z is 1 over exponential I theta, right? So we are considering z on the circle. So this cancels each other and has a very important formula, 2 pi I. So this is actually more important result than something 0. But we still need time to go to investigate further. So this is r equal to 1. Now we extend a little bit by considering the circle with a finite radius, say d theta. Now we extend the case to the circle of finite radius r, but centered at the origin. So this is this is r, x, y. This is theta, so c is r exponent theta. But this r is fixed. So what is the result? What would be the result of this? Then c z over dz. z is r exponential I theta I d theta, right? I think I forgot something here. So when we are considering the point on the circle, which is defined by capital R exponential I theta, this differential of dz, since R is fixed, only theta varies, so exponential I theta, I d theta, right? So this integral becomes 0 to 2 pi r exponential I theta, r exponential I theta, I d theta. And this again cancels each other, and become 2 pi I. So this result is actually same when the radius is finite, right? How about if it is not centered at the origin? Another case, more advanced case. Not centered at the origin, but z equal to z naught. Okay, so this is finite result. So again, we draw the line which is parallel to x. This is theta. Let's say z. So if we have a particular point z on this circle, which is centered at z naught, how do you represent this point? Z. This point z can be represented as z naught plus r exponential I theta, right? You have a circle with the radius r, which is centered at point z naught. And you like to describe the point on this circle, on the point z at circle, with the angle theta which is parallel to x. Then how do you define this point? It's simple, right? Z naught plus r exponential I theta. You just move this point to here. So just add this z naught, right? So from this, dz will be simply r exponential I theta, d theta I, and z minus z naught is r exponential I theta. So this integral c over z naught over dz. So this is c. 0 to 2 pi r exponential I theta, r exponential I theta, d theta I. Again, this cancels each other, and we have the same result, 2 pi I. Here, we note z naught include inside of the circle, C. Right? It's a very simple integration, so it should be easy for you. And now, study a little bit more complicated case, polynomial of z. So, most general case. Shall I go a little bit slower? So another case. Again, this point. Z naught with a radius of finite r. So this is your theta. This is your z. And we like to consider this particular integral. M, z minus 6 to m, z. M is an integer. M belongs to z, integer. Then tz, z is as before r exponential I theta, right? So dz will be r exponential I theta, d theta I, z minus z naught is r exponential I theta. So this integral is actually 0 to 2 pi r to the m exponential I m theta r exponential I theta d theta I. So I times r to the m plus 1 exponential I m plus 1 theta d theta. Now consider that. So m is an integer. So as a result, m plus 1 equals integer, right? So if we have a sine integer theta integrated over 0 to 2 pi, what do you get? 0, right? So when m is integer, it's always 0. How about cosine? And you integrate integer theta over this theta. Always 0, or there's a particular case? When m is equal to minus 1, then cosine is 0, is 1, right? And otherwise it's 0, right? So this is actually two pi delta m minus 1, right? So when m is minus 1, then cosine m plus 1 is 0. So cosine 0 is 1, so this is 2 pi. When otherwise is non-zero integer, then it's always 0. So the whole integral is again I r m plus 1 2 pi I delta m minus 1. And when m is minus 1, this is 0, so this becomes 1, right? So only meaningful result is 2 pi I when m is equal to minus 1, and I think I have I twice, so we don't need I here. So this result is actually 2 pi I delta m minus 1. So all the polynomial results give 0 except m equals minus 1. So this is quite unique because when m is minus 2, then it doesn't satisfy Cauchy-Riemann condition. So it cannot be classified, but you cannot be classified with the Cauchy's integral theorem. But nevertheless, this result is 0. So Cauchy's integral theorem states that only for the case when fz is analytic, then the integral is 0. But there can be other integrals which can go to 0. So this is very meaningful result. So for arbitraries, the C for the circle with the arbitrary radius z minus z naught to the m dz is 2 pi I delta m minus 1. So everything is concerned is true when that z naught is in the center of a circle, right? So far, we have considered the case when z naught is at the center of the circle, right? What if not? Do you think the result is still the same or is not? So let's consider another case. It's the case when z naught is at the center of the circle. So the question is, what if not? What if not the case? So I'm going to consider another case. There's some circle. For simplicity, we have ZC. So this is your center. Center of the circle. And this is your original C. So my question is this. When Z naught is not at the center, what would be the result? So far we consider the case where Z naught is at the center of the circle, right? But now let's consider the different case. So I'm going to make a little modification of curve like that. So let's say this is a new C prime. So C prime is considered of C1. It goes this way, C2, C0, C3, and come back. So C prime is considered of C1, C2, 0 plus C3. And we have a bit of M. So now consider this new C prime. It's a very complicated region, right? C prime is considered a part of original C with the region modified, includes this Z naught and coming out again. So I would like to ask a question that the Z naught is inside of this circle, this region, or outside of this region? Outside, right? So now, C naught is outside of this whole region. C prime. Then we can apply Cauchy's integral theorem, right? Then C prime should be 0, right? Because C naught is now outside. Zero by Cauchy's integral theorem. Right? And I'm going to need this part again. So let's make a copy of a big thing. And edit, add clipboard, and clipboard. Okay, so this, very nice. Oh, sorry. So let's use magnifier to look at that. So we magnify this region. Then this region will be looking like that. Right, C2, C3, and this is epsilon. So the closed integral C prime Z minus Z0 M to dz is what happens? C1 right? So C1 is the outer part, starting from here to there. And then it goes inside the C2. C3 is but this curve is clockwise. So starting from 2 pi to 0, right? So it's a minus of 0, z minus c to the m dz. We took the positive as a counterclockwise. So this is clockwise, we can put minus. And as epsilon goes to 0, what happens? If you close this region, epsilon, the small entrance, we close this 0, then what happens? C2 and C3 are opposite directions. They cancel each other, right? So C2 and C3 are opposite direction. So these two integrals will become 0. And C1 will become the original C, right? As epsilon becomes 0, then they are finally closed. Then C prime becomes C. C1 becomes C. So C1 becomes C. C1 becomes C. So we have the following result. C, z minus c to the m dz minus c rho c minus c to the m dz is equal to 0, because the original integral z naught is outside of this region. So this is a very important result. Even though this z naught is not at the center of this circle, the result is the same. This result is what? It's centered at z naught, right? So this result will be this. Oh, sorry. How do I go back? This will be 2 pi I delta m minus 1. So we have a very interesting result. So 0 is C dz is same as 0 is 2 pi I delta m minus 1. Even though z naught is not at the center of the circle. So it doesn't really matter. So this is a very important result. So now we know that. So any point still, if z naught is inside of this region, then the result will be same. I mean, whether it is center or not. This is very general result, right? In general, we have z minus z naught to the m dz is 2 pi I delta m minus 1. 네.
이게 0 equal
Minus. So I think I should write this way, right? The 0 has to be the difference between two integrals is 0. So as a result, when z naught is in anywhere in the circle, then this result should be 2 pi I minus times delta 1. So this result comes from the Cauchy's integral theorem, that when fz is analytic inside of some region, then this integral is 0, right? So we can modify the curve such that we can make some small indent of original curve to enclose the circle with a small radius. So this is a very important result. So no matter where it is. So you may ask why this is so important, right? Because this allows us to calculate this function. You can calculate this a to 2 pi a plus b cosine theta d theta. So the Cauchy's integral theorem actually gives this result, and I'm going to show soon to calculate this function. So even though you might have done many integrals in your high school days and also in freshman years, but this kind of integral is not common in concept, right? You've never seen this. But this actually comes from the real physical situation. Anybody remembers the year 1779? '89, July 14. It's the French Revolution. Date de Bastille. And so early 18th century, Europe was in war. And the one side was French, right? The other side was England. So French and England has been war in 18th century, early 18th century. And England has a very strong navy. French didn't have. But Napoleon wanted to conquer England. So I wrote some. So this is England. This is French. So this is London. And London is famous for the big difference in the tide. Tide is 조석 간만. So if you want to invade London with the French Navy, then they have to have accurate knowledge of the tide and particular date, particular time. So Napoleon asked Cauchy was a French mathematician at the École Polytechnique at the time, to calculate, to estimate, to predict the tide and particular date or particular time. Yeah. I mean, today it's a very easy problem, right? You can just use a MATLAB or Fortran or whatever computer can calculate very accurately. Do you know how the tide is related to the gravitation between Earth and Moon, right? So the height of the tidal is related to the tidal force is related between the gravitational attraction between Earth and Moon. So that tidal force is related to this simple formula, R minus R2 square, which is R1 square minus 2R1 R2 square, and some constant. which is r1 square plus r2 square minus 2r1 r2 cosine theta. Or depending on the angle, you can either use theta minus theta, either way. So in order to predict the tidal force of London, the Cauchy needed to estimate the following form of integral. So Cauchy needed to integrate 0 to 2 pi a to b cosine theta over t theta, because what you need is average. You have to average out all the radius of Earth and Moon, right? So you have to have 0 to 2 pi integral. So this is actually came from the original, the formula for the tidal force in London, and you can actually simplify into mathematical form for this equation. So if you can calculate this integral, then you can tabulate the A and B is of course complicated numbers depending on the distance between Earth and the London, Paris, and particular date, time, because Earth, the moon is circling around the Earth. So it's a complicated number, but once you can calculate this, then you can estimate the tidal force. That's the reason why Cauchy started the complex integration, because at the time they didn't have a computer at all, right? I mean, today it's an easy problem, but about 300 years ago that was a very difficult mathematical problem. So Cauchy converted his military problem into mathematical problems, and then converted into that particular integration. So we can continue that. So example is this. Say 0 to 2 pi a to b cosine theta d theta. Say a is greater than b. Let's consider that. So it doesn't. It looks like it doesn't have nothing to do with the complex integration, right? But we can take a look. Consider this. That's actually what Cauchy did. Consider z is exponential I theta. Then cosine theta is what? Z plus 1 over z. Right? Because cosine is exponential I theta plus exponential minus I theta. So exponential minus I theta can be considered as 1 over z. And dz is exponential I theta, d theta I. So d theta can be considered as I over exponential I theta dt. And this I z dz. So original problem can be converted into complex integral a to b cosine theta d theta can be represented as this particular integral c. So we have I z dz and a plus b 2z over 1 over z, right? So Cauchy must be real genius. So he converted the original theta integration into a complex integral, and so dz I az plus 2bz squared plus 2b, right? iz. So I'm putting this z here. So az to be z squared, and to be 1 over z becomes just b, right? So maybe you need to copy the whole thing for next page. Okay, let's just do this problem today and then stop for today, right? Finish it. Edit clipboard, and then I'm going to move next page. Previous page if I made any mistake before I proceed. So cosine theta has to be 2 cosine theta has to be z plus 1 over z. Oh, so actually I made a mistake. So it has to be one half, right? So it has to be in the denominator, then it becomes 2a and 2a and the coefficient 1, correct? So okay, so I think I'm getting very good now. Maybe a little bit bigger. Right? To be z squared. So I can put 2b out, so it becomes 2bi over 1 dz z squared plus 2b over a yes, cosine theta c plus 1, right? Something is wrong? Let's go back. I have to correct this. So this is not 2. This is not 2. 2. Not 2. It has to be in the 2 here. So it become 2, 2. Become 2, 2b. Correct? So that is 2 over bi, c minus c1, c minus c2, c squared plus 2a over b is z plus a equals 0. So z is minus a over b plus minus square root of a over b square minus 1. So C is a unit circle. I said A is greater than B, so 1, 2. So one of the point outside, inside. So this is C1, C2. So C1 is minus A over B minus square root of AB square minus 1. C2 is minus B plus A over B square minus 1, right? So this is a unit circle. So if we solve this equation, then we have Z1, Z2 from our junior high school days. So we know that I assume that A is greater than B. So one of the solutions lies outside of the circle. So only we have one inside. And we need to calculate this. C minus C1, C minus C2 is so we know that one of the solutions is outside, the other one is inside, and we need to make a fractional expansion of this form. C2 minus C1 is what? C2 minus C1 is twice over A over B square minus 1, right? So we can go back to minus C1. We have to copy this. So B2 over BI. My voice sounds a little bit funny. Edit. Clip that. Throw it away. So Z minus C1 is Z minus C2, A over Z minus C1, Z minus C2. So Z1 is minus 1 over Z2. It's less than 1. So Z2 is only inside of the circle. And how do you calculate the partial fraction? That's very easy. So A, you just want to make B disappear. So you multiply Z minus Z2 everywhere and set C equal to C1. Then B will disappear, right? So if we multiply Z minus C1 everywhere, what do you get? 1 over Z minus Z2 is equal to A plus Z minus Z2 over B. Now set Z equal to Z1, we have what? A is 1 over Z minus Z2. And then do the same thing for B. You multiply Z minus Z2 and set Z is equal to Z2. So in this case, we have Z minus Z1 is equal to A, Z minus Z1 times Z minus Z2 plus B. If we set Z is equal to Z2, we have B is equal to Z2 minus Z1 over 1. So if you use this space, maybe use red wine, let's call it. So 1 over z minus z1, z minus z2 is actually z2 minus z1 over z minus z2 minus z minus z1 over 1. And if you go back, so twice of z2 minus z1. So our integral go back. Okay, I think I can memorize. Times Riemann. Okay. We don't need this. So this is the original integral. Oops. And twice over minus 1 So now this is a unit circle, C2.
So what happened to the second integral? It's outside, right? It's 0. So we only need to concern about this. This is 2 pi I.
So this is 0, this is 2 pi I. So the result is simple. This I and I cancels each other. 2 over bi, 2 pi I, twice over a over b square minus 1. So I cancels each other, 2 cancels each other. So it becomes 2 pi divided by a square minus b square.
That's what Cauchy obtained in early 18th century. Without having to use a computer, he just used one theorem, Cauchy's integral theorem, and he obtained the very complicated integrals. Well, this integral is actually even hard today to do by hand without, if you don't know the complex analysis. You cannot do this, you can obtain this result, right? So the Cauchy did about 300 years ago using very nice theorem called Cauchy's integral theorem. So at that time, for 17th, 18th centuries, So complex analysis was like a supercomputing tool for them. And even though we have a very proficient technology, very high technology, still we need to learn complex analysis, and that's the reason why. So maybe I'm going to stop here today. And actually this part also is covered in the quiz. So I'm going to post my YouTube class and also PDF file today